In this video we're going to look at the binomial distribution and how it relates to the normal distribution. In particular, we're going to look at some computational problems that we have with the binomial distribution when the number of events is very large, and how we can then turn to the related normal distribution to actually calculate some probabilities. Let's do that with this example. You have an unbiased die and you roll, or some dude rolls this dice 600 times, and more than 120 sixes are shown. Let's pause for a second. That's a lot of sixes. How many dudes do you know who roll this many sixes? Well, not many. Let's find out exactly how many though. We can model this situation by a discrete random variable x, which is binomially distributed. Let x be binomially distributed. There are 600 random events, and the probability of success in one of those events is 1 in 6. And I've given some rough probabilities over here, just visually in terms of boxes. If I asked you to calculate the probability of exactly 119 sixes, you could do that. The probability that x is equal to 119, you could do it in theory, is 600, choose 119, times the probability of success. So we have 119 successes, and followed by 600 minus 119 non-successes. So I can write this number down, but the denominator here is 6 to the power 600, which is huge, and it will just break your calculator if you try and even attempt to put that in there. So while I can write down what this probability is, calculating it presents some difficulty. And in particular, if I want to calculate the probability, so what we're actually asked is to find the probability that x is greater than 120. If I actually want to calculate this, then I have to sum up all these boxes. So not that one, but this one, all the way up to 600. I'm calculating all these boxes of very small height. Well, I'm calculating the area of all these boxes of very small height. And that's going to get me into trouble. I mean, even if I could calculate these things, the error would be so big that it would just wipe out any accuracy I was hoping for. So instead, we turn to the normal distribution. So there's some good news. The binomial distribution is related to the normal distribution. In fact, the normal distribution goes through the midpoints like this. So this is a new random variable y, and its probability density function goes through all these things. So this is the probability density function for some new random variable, which I'll tell you about in a moment, which cuts through the midpoints of all these boxes. So we'll let y be normally distributed with the expected value the same as x, mu, and the variance the same as x. And that gives me this line here. All I need to know is what the variance and expected value of this thing are. Since, well, the variance is easy to calculate for a binomial distribution, it's 600, sorry, this is the expected value, it's 600 times 1 on 6, which is 100. And this is roughly the number of sixes you would expect to see if a fair dice were thrown 600 times. Good. We also have sigma squared, which is given to you by the formula 600 times the probability of success times the probability of not success, which is 500 on 6. So sigma itself is equal to 10 root 5 on 6. Excellent. So now we have to convert from this random variable into a question about these ones. So recall what I'm trying to do is I'm trying to calculate this area here. This blue area, including that bit up there. Like this, for all the boxes off to 600. So what I'm going to do is approximate that with this red curve, and I'm going to take the area not from 120 or 121, but from 120.5. That area giving me a slightly better approximation than if I was to start from here, because I'd miss out half of that box. So we'll say that the probability that x is greater than 120 is roughly the same as the probability that y is greater than 20.5, or 120.5. Good, good. Now you may recall that this is a normally distributed random variable. It's got some funny expected value and variance. I need to convert this into the expected value and variance of my table, which is this has to be 0 and this has to be 1. So what I have to do is calculate the probability. First of all, I recenter this so the expected value is 0. So I take away 100. So that's y minus 100 has to be greater than 20.5. And then I divide through by sigma. So this is the probability that y minus 100 over sigma is greater than 20.5 over sigma. Okay, so we've mushed things around a bit, but the important thing here is that this random variable, y minus 100 over sigma, is normally distributed with expected value 0 and variance 1. And that means we can look this up in our table of numerical approximations. So this here is equal to the probability that z is greater than that thing, and you'll need your calculator to tell you that that's about 2.25, where z is normally distributed with expected value 0 and variance 1. And you can almost look this up in your table of probabilities. That's 1 minus the probability that z is less than 2.25. Good. And this is what's contained in your table of numerical approximations. That's z. I go down here until I get to 2.2 and across to 0.5, and that's 0.9842. So that's 1 minus 0.9842, which is 9842? No, 9878. 9878. 78, which is about 0.0122, or about 1%. So, how many dudes roll like this? Well, about 1% of dudes roll like this, and that's not many. Thank you.